All right, well, I hope this isn't going to be like an incident, you know? Like a BOL incident where things don't load. Okay, might as well start talking while I'm waiting for that to load, because we have so much to discuss. You know, we're still talking about relativity and quantum theory. Yeah. No, it's not happening. Okay, because I can hear you guys talking. I just can't hear me. Okay, how's that? That is good. Is this just going to just keep happening? Because between this and general relativity, I just can't take it. Sent mail. Can we just do sent mail, please? I mean, is it going to, okay. Okay, so we touched on this on Thursday, but it's kind of a key point to understanding modernity. It's this notion of subjectivism, and how subjectivism, that idea that everybody looks at things from their own point of view, that it's, depending on your beliefs, impossible to really reconcile all those points of view and come up with a single truth. We can't do it. Ergo, we're all individually locked in our own private Idahos. So this was not the idea of the nature of science in its initial stance, right? The initial stance of Descartes was a kind of empirical and metaphysical, well, metaphysical and rational certainty. The stance of Locke, even though he got rid of a lot of the metaphysics, he still firmly believed that, hey, reason is a procedure. Reason is also a procedure that's guaranteed by God. So if you get educated, you apply yourself diligently, you will be able to produce the kind of truth that other agreeable, reasonable, diligent people can agree on. And the discourse in which we are going to all enter into this sort of consensual, intersubjective debate about objectivity is going to be scientific. So even though we've talked about a certain degree of subjectivity in science so far, because, hey, we're human beings, we're subjects, and now we are the masters of knowledge. So when we refer to our own cognitive authority, when the point of view is from our point of view, it's subjective, but it's not hopelessly and radically subjective. It's the kind of subjectivity that can still work its way towards a shared truth. Well, what happens? By the end of the 19th century, to relativity. By the end of the 19th century, subjectivity is getting more radicalized. Victorians are slowly starting to surrender the notion that there is some sort of objective truth out there if we could only reveal it. This trend was no more pronounced. We're used to seeing it in things like, you know, modernism and literature like Mrs. Dalloway, Virginia Woolf, these sort of stream of conscious narratives that are associated with the fin de siècle, where you have this powerful constituent of reality is not what's happening out there objectively, but in Mrs. Dalloway, the narrative is pushed along in the sort of random stream of conscious point of view from which we actually end up assembling the bits and pieces of our lives that make up our story, but have less and less to do with the collective story or the collective truth we're all telling. By the end of the 19th century, early 20th century, this fin de siècle period, they are already onto that. We associate this with modernism. We call ourselves modern. And we see that in literature. We see that in art. You know, when you start going to see Kandinsky and it looks like just a bunch of sort of wonderful, expressive splatter on the canvas. Nowhere was this more pronounced, actually, than in science. Because scientists were beginning to think, scientists like Ernst Mach, beginning to think in the late 19th century, hey, you know what? I agree with this whole empirical sensory thing that we need to absolutely value sensory data as it's coming on board our minds and we're thinking about it. But let's not make this naive mistake that these Victorians made. Remember those Comtean positivists that the Victorians were? Remember Comte that said, now that we're all scientists, now that we use empirical knowledge, it's the end game. We're as high as we can get, and this is the final, most advanced stage of civilization. His assumption is that what you're seeing, what you're observing, is true, that it's all real, that there's some kind of objective reality to your mental representations of the things you see, touch, taste, and smell. There's a conflation of the object out there and our subjective representation. Sloppy thinking. But this kind of thinking comes under severe scrutiny in the late 19th century, like I was saying, with people like Mach who start thinking, you know what? What we're really observing when we observe reality are the sensations that arise in our minds due to the impress of the object on our senses. So we're not studying the objects themselves, we're studying the sensations that arise as a result of whatever these things are. Can we even call them objects? We have no idea. What the objective nature of this world out there is, we don't know. Because really what we experience is the intersection of our cognitive sensibility, right? Our input of sensory data and our sort of psychological construction of what that data means. Congratulations, science. You are no longer describing the sum totality of this real universe, but you still have a lot to tell us about the rules that govern the behavior of these sensory stimuli. So science isn't, totally involved in a vain endeavor, but do you see that's a bit of a step back from knowing absolute reality to knowing the cognitive sensory representations of reality? So subjectivism is already beginning to reign on the parade of human consciousness, human pride, human sense of we can know everything. Those colossi astride the 19th century, those sort of vain people, like you read a little bit of Myers and Oliver Lodge, and even Freud comes out of this sensibility, and Marx certainly comes out of this sensibility. Let me give you an ideology, let me tell you how it is, right? I can explain the sum totality. That is an attitude that is simply almost not going to be sustainable anymore with the new kind of radical skepticism we get in the 20th century. So I just put little bullet points about subjectivism, which is, can we really share a frame of reference? Because if you're viewing the world according to your psychological representations of your sensory data, and I'm viewing the world according to my psychological representations of my sensory data, those are two such separate subjective instruments. I mean, are we even inhabiting the same world? What is your experience of reality anyway? So given this sort of flawed nature of our subjectivity, is objectivity possible? Can we meet in the middle somewhere? Can we share a point of view and be objective? It's more and more difficult. And what this means for science is that science surrenders any, not only metaphysical aspirations, right? Like science was willing to say, by the time we get to Locke, and certainly by the time we get to those Enlightenment materialists, you know what? Let us be in charge of describing nature. And supernature, let's leave that to faith and leave that to God. However, now look what science is saying. Don't know anything about the supernatural. Can't really tell you I can know anything for sure about nature either. All I can give you is a psychological description and some rules by which we can interpret and organize that sensory data. So massive contraction of the claims of science, but at the same time, what century has been more productive in terms of its scientific achievement? So there's an irony here. Science contracts in terms of its knowledge claims and radically expands in terms of its achievements. Which I'm just going to throw this out as a kind of interesting point. That means it is tempting and seductive always to identify science as this forward and leading edge of human progress and human development because it rapidly transforms the world in visible, impactful ways. However, at the same time, you're chasing after something that says, I'm kind of leading you down a blind alley. I can't really tell you anything ultimately real. And that's why when you're reading your Owen Gingerich, you desperately see that there's some scientists who still have this theological bent that understand, that are still trying to see if science cannot actually tell us something more fundamentally real, something of more profound value. And then my last bullet point says, is there no hope of moral or theological message from nature? Well, this would just mean that once human beings tried to get control of knowledge of nature, remember we had the scientific revolution in the 17th century, and quickly in the wake of that, we had all sorts of political and social revolutions. We had all sorts of humanistic sciences developing to define the parameters of what it means to be a human, the ethics that should be attendant upon that humanity so described, that knowledge of physical nature was actually providing a basis for all sorts of other ethical and moral insights. Now you don't even have knowledge of physical nature, so can science give us ethical insights? I think you get the picture. It's kind of grim. Now, add to that special relativity. Add to everything I just said, the loss of the ether, the loss of subjective, like a kind of sense that subjectivity can ever enter into a shared frame of reference, and the coup de grace, sort of the metaphor that sums this all up is that, oh, and guess what? According to your frame of reference of your inertial motion, you actually experience things like intervals of time and intervals of space differently. That's how alone you are. Your psychological reality isn't just in here. Even the physical nature of reality itself, the structures are flexible and changing according to the subject. So this is a kind of corrosive subjectivity that has entered into the very structures of reality. Now, we kind of raced through this, and we're not going to spend too much time because it's just a wormhole that you can get into. But cool stuff about special relativity. Remember, we talked about can't think about space, can't think about time as fundamentally separate. We've got to think about space-time, okay? And that the top speed, top progress you can make through space-time is the speed of light. So we had Tweety over here, and she decided to stay on the planet Earth, going 0 miles an hour. We had Norton getting in his super revved up airplane, deciding to go 600 million miles per hour, expecting to catch that light beam. Of course, he never does. The light beam proceeds at 186,000 miles per second, or 670 million miles per hour, just like it was when he was standing next to Tweety. Bizarre? Yes. Now, if we put this on a graph representing space-time, we'll just sort of parse it and see how we can make that make a kind of superficial sense. All right, 5 years go by. Norton's gone for 5 years. We know that Tweety's just been sitting in the parking lot. 5 years go by. All of her 5 years spent advancing through time. Tweety's 5 years older. Norton, only part of his progress, he can't go at the speed of light, but he's approaching the speed of light. So part of his progress is through time. Part of his progress is through space. So let's say he's been gone 5 years, but he's only aged 2, because only 2/5 of his progress was through actual time. What happens with the light beam, the speed of light? If you were traveling, if Norton had managed to get that airplane up to the speed of light, which of course is physically impossible, if he had, he would have been ageless, right? Because all of his progress through space-time would have actually been through space. So in that period of 5 years, a beam of light will go 5 light years. A person sitting in a parking lot will advance 5 years in time. And a person traveling somewhere near the speed of light will advance more slowly through time and make more progress through space. So these are all relational. These are variables that are meaningful in relation to each other. Space and time are inseparable, and as variables in an equation, they always equal the speed of light. So no matter how fast Norton was going, he always saw the speed of light, saw light travel at the speed of light. Now, just to get our minds working from a familiar to a strange way, right? And I talked in a rushed way about this, so I'm going to talk in a rushed way about it again. But I want to go to Palm Springs. It's 90 miles. In our reality, 90 miles doesn't change. Space doesn't change. What are the conditions I can control? I can control how fast I go in that car. I can control my speed. And that will affect the amount of time it takes me to get there. But time for me will pass at the exact same rate as time will pass for the person in Palm Springs who's looking at their watch waiting for me, right? So the real variable there is speed. But let's turn this around. We know that with special relativity, the one thing that doesn't vary is the speed of light. Okay, by our own logic, speed doesn't change. What's got to change? Oh, the intervals of space and time. So the actual constituents of space-time have to change in order to preserve the speed of light. Bizarre and fascinating. So basically, special relativity is letting us know that temporal, that's time, or spatial intervals, right, they're not concrete things that exist outside of our experience. They don't provide this gigantic frame of reference in which we're all moving, right? They're relative. You are moving at a certain inertial speed, uniform motion, and you will therefore progress through space and time at specific intervals specific to your momentum. And someone traveling at a different speed is going to have their own, make their own progress through space and time based on different intervals. Now, this is not to be confused with experiencing it differently in your brain, right? If I get on that rocket ship with Norton, okay, and we're going, according to Tweety, you know, if she's watching us, we're moving really slowly, right? Because we're moving through time in a very slowed rate. Are we going, why am I talking so slowly? Why is it taking forever to walk across the room? No, we are experiencing, as far as we're concerned, nothing has changed. When we're traveling in uniform motion, we don't notice any shift going on in these intervals of space and time. We don't experience them, but they must have changed because even though I'm going 600 miles per hour now, light's still passing me at the same 670 miles per hour. Something must have changed since I was standing still with Tweety in the parking lot. Okay, we just have to accept people. We just have to accept and move on. Funnily enough, Einstein calls this invariance theory. So we call it relativity, but he calls it, originally wanted to call it invariance theory because what never varies? The speed of light. That was really cool because even from the beginning with Galileo's introduction of the laws of motion, relative motion and relativity in general was part of modern physics. This was new, right? They expected light to change speed. They expected, right, if light was able to combine the speed of light plus the speed of the Earth moving through the ether, they thought it would be 186,000 miles per second plus however fast the Earth is going. They expected it to be relative. The big discovery, it's invariable. And the things, the three big sort of mind-bendy things that happen that sort of trash our lovely shared objective framework in which we all sort of exist in the same context. Time dilation, right? Seconds pass more slowly. It still feels like a second to me, but my second is passing more slowly. And I'm going to remember we had this oh so disturbing example of the atomic clock. And the atomic clock is a clock where you got a photon bouncing backward, up, down, and getting registered by these photon detectors. And every time it goes and returns, that's 1 second. Take that clock, put it on an airplane going really, really fast, and you notice that by the time the photon wants to return to the top of the detector, oh, detector's over here. So now the photon has to go like this. Except a second still only counts as the amount of time it takes you to go from one detector to the other detector and back again. So according to the clock, you have been gone, X amount of seconds, right? But the clock on the planet, right, the clock at the airport might have said, oh, 5 minutes has passed. But the clock that had to travel all of this distance, that had to make this diagonal motion in order to complete the single return between detectors, that clock has only been aged 3 minutes. Now, this experiment has actually been done, obviously not at speeds even remotely approaching the speed of light, so the difference was incredibly infinitesimal, but it was there, and it was measurable. This stuff is real. It's constantly confirmed in prediction after prediction. It's a solid physical theory. The other weird thing that happens, but let's not get our head in a vice over it, is objects appear foreshortened in the direction that they're moving. So all sorts of freaky things are happening. I'm still in the parking lot with Tweety. I'm watching Norton race off in the plane. And to me, it looks like his airplane is contracting. And maybe he looks like he's getting a little bit, I can't say skinnier because he would actually be compressed in this way, so he'd actually hit stock here. But it looks like he's being foreshortened. So even the structures of matter are going to be impacted by momentum. But like I said, let's not get all bent out of shape about that. Let's get bent out of shape about general relativity. And then here's the third problem. Let me just put this simultaneity. When you say if an event happens and it's real and it's now, that we should all be able to objectively agree that it happened? I mean, that's our old notions of causality. We have two figures in here, right? And horror of all horrors, look like they are drawing weapons on each other, right? And they're going to blow each other's brains out. So in a shared framework, we would all see them draw their weapons, fire at the same time, and maybe kill each other at the same time. That would be causally significant with a significant outcome. But it turns out, depending on what point of view, inertial motion we're traveling at, we might actually see one of these people die before the other. One of them draw their gun before the other draws their gun. Hey, that's cheating. We will actually see the events in space-time unfold in a different way. Gosh, that's going to be really, really hard to make a moral judgment about what happened. I mean, isn't it important to know if somebody pulled a gun before the other person had a chance to pull their gun? That would make a sort of simple, respectable duel, turn that into murder. So there's all sorts of problems, sort of moral and ethical dilemmas that are just sort of saturating special relativity in terms of how can we all be morally responsible for each other, morally responsible, if we don't even share the same sequences of causality on which you determine right and wrong. Do A, get result B, decide whether A was good or bad. How do you do that? So there's subtle ways in which this scrambles. And just to explain the physics of that, let's say you can take a big chunk of space-time. Remember, we're not allowed to have just space. We're not allowed to have just time. And what is time anyhow? Time is just the order in which certain events happen, right? So say I knock over this cup. There's going to be a certain order. It's here, it's here, it's here, it's here. Is there some magical flowy thing called time outside of that? No. Time is the directional arrow, the sequence in which this happened. So I can take this whole chunk of space-time here, and this whole chunk of space-time will contain the beginning of the sequence, hey, coffee cup standing, to the dreaded end of the sequence, hey, coffee cup spilled and empty. And that is time. But remember, we're all going to experience time differently. So say we have here observer A. He's standing on a platform. Let's say these two people, I think in your reading, they're on a train and the train is pulling out. So they're on a moving platform. We know from the point of view of observer B, let's say this is the train, okay? It's moving this way. One guy's facing here, one guy's facing here. They're going to shoot each other. And, you got the observer who's right in the middle. So they both get the signal to draw and shoot at the exact same time, according to this guy right here, fair fight. But what about me? Say I'm figure A. I'm standing over here, and the train is pulling away. I see the events happen in a different way. My slice of this big time cube, this space-time cube, I angle it in a different way. So the events happen, oh, it looks like this guy's just standing there while the other guy's starting to pull his gun because this guy got, according to my point of view, I see the person draw his gun. The person who draws his gun first is closer to me. I see this action before because the light has less distance to travel towards me. Whereas the guy he's shooting is a little farther away from me, right? So even though he, according to the person on the train, pulling it at the same time, I see these things as happening at different instances. So do you see that special relativity is a drag in terms of fundamental principles of our shared notion of reality with sort of implications even for morality and truth. And those are, so we have just to list them again, we've got time dilation, we had the contraction of matter, and we have no true simultaneity, no true shared reference. All right, so moving on, we already have special relativity being kind of disruptive and a drag to the Victorian sensibility, because all those things are so important to those 19th century moderns thought modernity was going to be a time of technological splendor where science, truth, and beauty were united in the same project, where we would all find these sciences. Maybe it would be evolution, maybe it would be eugenics, who knows what they were trying to pull off, maybe it would be psychiatry, but somehow science would erect the superstructure of what is true, what is morally true, what is really true, and suddenly that's just not the gig anymore. Now, I'm not going to actually talk about general relativity because it's just way too complicated, but just to encourage you to find out about these things on your own, you know, you can't, everything we've been saying about space and time has in a way been superficial, because it's one thing to say space and time relative to each other, or, you know, as an equation cannot go faster than the speed of light. It's another thing to go, really? Why? Right? And of course, that is a question that Einstein was asking. And he also, special relativity doesn't include this huge thing called gravity. You know, Newton told us it was uniform and everywhere and a property of all matter. So it's like a little inconvenient to have a theory that excludes gravity. But he comes up with this very interesting way of understanding the universe. That classical universe is infinite and shapeless. Remember Descartes' universe? It's just a big grid. It's shapeless. It's infinite. You are actually living in a finite universe. You're living in a finite universe that has a specific shape. Hold on. Where does it derive the quantity that defines its finitude? Where does it get its shape from? There's a finite amount of mass and energy in the universe. Finite amount of mass and energy. And depending on the distribution of that mass and energy, on its concentration, how it exists in relation to each other, that's the shape of your universe. So the shape of the universe, yeah, the universe, space-time, it's curved, it's weird, it does funkadelic things. And the way we're going to understand the shape of this universe is that we're going to take this idea of space-time, of special relativity. And we're going to take Newton's principle of, okay, I get it, universal gravity, and it has this amount of, this calculation for its force. And now we're going to look at gravity not just as a force, but literally as the spatial geometry of space-time, right? That space-time itself is an expression of this shape of the universe, right? And because that shape of the universe is constantly warping, bending, twisting, whatever, that space-time also, like if I took a Euclidean sheet that is perfectly flat and, you know, it's got its 4 grids, and suddenly I stretched it and warped it because I put a lot of mass here or a lot of mass there. Now, if I'm being stretched and warped with space, I don't notice that anything's happening, right, if I'm in uniform motion in terms of special relativity. But once you've stretched and warped space, can you see how the units of space have changed? And since time, all time is the rate at which the sequence of events unfolds. The amount of time it takes this cup to turn over from here is really about the sequence of events. Time is not anything that can't be described in terms of the unfolding of events in space. It can happen really rapidly. Same events can happen really rapidly. Same events can happen in a much more slow way. Time is contingent. So let's just not get our brains burst, okay? So let's just wrap this up because rabbit hole is widening. And then, of course, this makes the whole E equals mc squared thing profoundly relevant. The fact that energy and mass are interchangeable. You know how everybody's saying, ooh, it's all energy. That's what we are, we're energy. Well, you could also say, oh, energy, that's what it is. It's all mass. It's all mass. So they are actually interconvertible phenomena. And just to throw the other sort of weirdness out there, notice how if you are orbiting in space, you've got this inertial momentum going around the planet, and it perfectly counteracts the gravitational force of the Earth. That's weird. They're the same. Inertial, the force of gravity and the force of this accelerated motion in relation to mass are almost identical. So another way of thinking about this is when you're traveling in the car, when you're speeding, oh, I didn't even finish that thought, I'm so sorry. The people are floating is the point. Because gravity is being canceled out by the inertial momentum of going around the planet, what's happening? They're floating. You know how their muscles atrophy? They actually have to do exercise to keep their muscles bulked up, the astronauts, because there's no gravity. You have a certain muscular skeletal strength based on the amount of gravity you have to contend with on this planet. Well, what if I cancel gravity and I put you orbiting in space? You are going to turn into extremely powerless, weak little frame is going to just atrophy because you remove that level of resistance. So the other thing to help you appreciate this is that if you're in a car, you can be going 75 miles an hour. You can't even feel that you're moving, right? But what happens when you accelerate the car, right? You're actually accelerating, so you're getting more and more linear momentum. You're going faster and faster in a forward direction. But what's happening to your body? You're getting pressed against the back of the car seat, right? If you're in an airplane, you could really experience that. If you're in a fighter jet, you can experience that as G-forces, G1, G2, G3, G4. You know, even on some of these really fast roller coasters, feels like gravity. Feels like weight pushing you down. You feel really heavy. So acceleration and mass, gravitational, the experience of gravity and the experience of acceleration can both cancel each other out, and also when you experience them in the terms of moving, advancing through motion, or experiencing more and more gravity, they are also identical. So crazy. That's general relativity, and like I said, that is just to put that out there in case you wanted to have a more satisfying understanding of relativity than just special relativity. Quantum, now it's just going to get, we're just going to relax for a little bit because we're going to go back to the 19th century and some of our older friends that weren't quite so crazy, like J.J. Thomson. Remember, this is a picture of the Crookes tube. What we're going to talk about now is the other thunderbolt of scientific revelation that occurs in the 20th century. We're not just people living in a universe recarved by special and general relativity. We are people living in a universe retooled by quantum mechanics. What are those? Well, what is so interesting is that the early pioneers of quantum mechanics, the people that sort of brought it home to roost, in the earliest phases were members of what organization? The Society for Psychical Research. One of the key instruments to discovering the existence of the electron was actually J.J. Thomson, using Crookes' tube. Remember, Crookes had that evacuated glass tube, and he introduced that cathode ray, and he thought, oh, that must be a stream of radiant matter. Oh, that is so cool. Look, matter is not only acts like matter and mass. Well, they didn't talk like that. It acts like matter. Matter here is also acting like energy, and he called it radiant matter, and he thought, wow, this is so neat. I've finally broken that forbidden duality, right? That duality, that Cartesian duality. Matter is inert. Took these people forever, if you remember, to get rid of the spirits animating matter. Remember Aristotelian physics? Aristotelian physics where water moved downhill because it wanted to, where fire rose because that was its desire, where you explained motion of mass according to these psychological elements of the elements, right? The psychological aspect of the elements. It took scientists so long to kick this spiritual, psychological energy out of the universe. And then William Crookes, because he's romantic, because he doesn't like the idea of shutting spirits out of the world, says, oh no, I think there might be a radiant, energetic, or secretly spiritual aspect to matter. That is naughty. That's a no-no. And that's what the people at the SPR, the physicists at the SPR, were so drawn to. But do you understand that that is a sort of infidel statement against modern science? Or is it? Because that is exactly what's going to happen in the 20th century with quantum mechanics. All of that strange, mystical, nonsensical properties that we tried to chase out of the Aristotelian cosmos are going to enter back in through quantum mechanics. And it shouldn't surprise us that the people holding the door open were the SPR, Society for Psychical Research. So J.J. Thomson, using Crookes tube, trying to understand what this radiant matter really is, looks and interprets what we now know as a stream of electrons. And he says, whatever this is, it's got an electrical charge. It's got some kind of profound negative charge. I know that because it's racing towards the positive anode at the other end of the glass. But it can't be matter. It just doesn't have enough mass. The way it's bending in the presence of a gravitational field, there's just no way. It's got to be a mass particle that's even smaller than an atom, smaller than matter as we know it. He discovers the electron. He names it. He determines its mass, m, and he gives it an electrical charge. Wow. We finally know that there is a world beneath the world of atoms, a world within a world, a mysterious world that seems to be a world where energy and matter are in a strange state of flux because those electrons are doing weird things, right? They're making the back of the glass of the Crookes tube glow. I mean, they're just doing crazy things. They're involved in this auroral spectral light of glowing gases. What is this stuff? The other major breakthrough, and Röntgen also was a corresponding member of the Society for Psychical Research, and they're really open to this idea that crack open an atom, there's more going on in there. I think there might be some energy in it. And remember, energy is a totally loaded word for these people. They don't know what energy is, but remember that whole romantic notion? Energy exists on a continuum from just purely mechanical to strange psychical, mental, and spiritual forms. So it is potentially loaded to put energy back in matter. What is this guy doing? He's also playing with Crookes tubes. The people that wanted to find out about this energy, this mysterious energy in matter, were always using Crookes' radiant matter tube, his cathode tube. And what he finds out is even though he's got this cathode tube, he's wrapped it up in tarp, and it's sitting in the dark, he finds out that rather than making the end of the glass of the tube fluoresce green, remember that when you look at that Crookes tube, the end of the glass is glowing green because the electrons are hitting the back of the glass and knocking other electrons off, so it glows green. Something even weirder happened. There was a barium screen outside of the tube, and the tube itself is wrapped. It's in glass, it's in the dark, it's wrapped in this black tarp, and yet the screen is glowing. That means whatever was inside the tube got outside the tube, traveled through the air, and impacted this screen and charged it with, he didn't know if it was light, he thought it was related to light, but caused it to fluoresce. So this was a discovery of X-rays. He didn't quite know what they were, but this was a form of radiation that can do things that light can't do. It can travel through wood, right? It can travel through substances, and here's a picture actually of the first X-ray. His poor wife, right? That was her hand. I hope she kept it. And he was a doctor at the time, so he's able to show that whatever this X-ray energy is, it is freaky, and it actually doesn't just reflect, right, or diffract off your hand. It actually goes through your hand and can take a picture of the inside of your hand. Madame Curie, did you know the Curies also corresponding members of the SPR? And she was involved in the study of radioactive polonium. And here it was clear. She has this matter, polonium. She discovered it. and she gets the Nobel Prize for this. But radioactive polonium has this really weird quality. It's emitting energy and particles. And it's coming right, you can just see it coming from the atom itself. It's not coming from the cathode tube, which was weird enough, right? This is actually coming from the matter itself. So this is like a slam dunk that there is a subatomic world full of strange energies, and the energy must be in the matter if it's coming out of the matter. So we're sort of on the brink now. Thanks to our SPR affiliates, we're on the brink of subatomic physics. Planck is very important. Planck is examining black body radiation, where you can heat up a black body and then have it, which would absorb all of this energy, and then watch it emit the energy in the form of radiation. But the freaky, funky thing was, this energy that was emitted didn't seem to emit as radiation. What is radiation? Is a wave, right? It's a continuous, has a continuous property. Whatever was coming out of that was coming out in discrete quanta, right? Discrete lumps. And so he noticed that the lumps, the quanta, were actually coming out, and these were actually photons, were coming out, and they had different light waves, right? They had different color signatures depending on how much energy was being emitted. But it wasn't like there was a halfway point between the two amounts of energy. It would either emit one unit of energy or then jump to the next unit of energy, and each level of energy had its own kind of wave frequency or color. So this was considered very bizarre. But what became obvious is that matter was actually absorbing and giving off energy, and it was doing so in discrete lumps. I didn't know energy came in discrete lumps. I thought energy came as waves. So whatever it was, this actually completely challenged the notion of continuity in the universe. The idea, if you are standing at 4 and you want to get to 6, doesn't it make sense you have to go through 5? If you don't go through 5, you've done something really weird. You've dropped out of the universe at 4 and reappeared into the universe at 6. You're not How do you get from here to here if the universe isn't a continuum? All right, so this was a very, very bizarre idea that even though it's energy, and it's radiation, it's got this weird particle aspect because it's behaving like quanta. And that quanta of electromagnetic energy was soon labeled the photon. But let's think about it for a second. The idea that light is a wave is a really old idea, and it goes back to Young's double-slit experiment in 1802. People were saying, no, I think light is a series of particles. No, I think light is a wave. He does this experiment where he sends light from a source through 2 slits onto a screen behind the slits, and what he sees are wave patterns. That means light is a wave because it's got peaks and troughs that are overlapping, interfering with each other, and creating a spectral band of black and white and black and white, light and dark, light and dark. It's a wave. Case closed. All right, after we get Planck telling us that, I know it's a wave and it's radiation and it's energy, but did you know that energy has this weird particle quanta aspect? So they release light in the slowest, this is 1901, they conduct this experiment, they are able to get a very, very low level of light, so low that it's just emitting in those little quantized bursts. And they find out, wow, same diff. Even though I'm releasing light as like these little quantized packets, it's acting very much like a wave. So light is a wave, but a wave, an energy wave, has a particle aspect. Einstein is looking at this fascinating discovery of Planck's and going, are you kidding me? Energy is getting into an atom and then energy is being radiating back out of an atom? You mean matter and energy are somehow interchangeable, doing a constant do-si-do? What does this mean? Well, this was his paper on mass energy equivalence in 1905, one of the most famous formulas in science, right? We've all heard of this, E equals mc squared. The relativity principle in connection with Maxwell's equations demands that mass is a direct measure for the energy contained in bodies. So mass is a measure of energy, and energy is a measure of mass. E equals mc squared. And then he has this idea that I cannot, he writes in his journal, this thought is amusing and infectious, but I cannot possibly know whether the good Lord does not laugh at it and has led me up the garden path. So the thought that light transfers mass and that mass absorbs energy completely breaks the wall between energy, matter. Remember that strict Cartesian dualism that was going to make the world mechanistic and regular and make you understand causality? I'm just going to emphasize this point about when I keep saying Cartesian duality, I mean, remember Cartesian mechanics, that how strict Descartes was? He said, look, all the motion in the world, all the energy comes from push, pull, contact forces. That means if something's happening, it is not that difficult to understand. If you could see these corpuscles more closely, you would see they're actually touching each other. If I knock over this cup with my hand and I touch it, that is mechanical force, and you get it. You get why that cup turns over. But it needs a lot more explaining how, say, if this cup just tipped over because we magnetized it and then put it in a strong electromagnetic field and then you tipped it over from over there. All of a sudden we're getting into like freaky causality. That's complicated. Our rationalists, our mechanists of the 1600s and 1700s couldn't afford that kind of trouble. They didn't want spirit in the universe. Why? Because that would be an entree point for God. Too much mystery in your physics means you can't explain what's going on. That means who's going to explain for you? The church. Who's going to get power? Priests. Who's God on the side of if you're a French philosophe? He's on the side of the kings and the priests and the aristocrats. So do you understand that this kind of mechanical causality was a very, very big deal to science? And now you're starting to get causality that is just bizarre and inexplicable. Like scientific explanation seems to be losing its clarity as it gains tremendous wonder. Now Niels Bohr takes this idea a very important step further, right? J.G. Thomson knows that they're electrons. Planck and Einstein, they're all working on the fact that, well, we know the electrons are somehow in the atom, and we know that they're absorbing energy and emitting energy, but what's the structure? What keeps them in the atom? I mean, why don't they just go flying out of the atom, or why don't they go just crashing down into the proton? You know, they're negatively charged, the proton's positive. I mean, what's going on here? And Bohr says, well, he gives a very sort of simple piece of structure to the atom. He says, let me explain what's happening. Electrons actually exist in these stable orbits that circle, you know, the proton and the nucleus. So they're in orbit. And what's happening when you see energy being absorbed by an atom? What's actually happening is these electrons are like, you know, buckets. They can take more energy in, but if they do, that means they have to jump to a higher state. They have to go to one orbit up. There's, you know, multiple orbits that are circling this nucleus. So if they lose energy, the electron drops one level down. So you got this really interesting picture of an atomic world where electrons are explaining, we can explain the absorption and emission of that weird quanta of light. and weird quantum energy in and out of an atom merely through the activity of the electron. Jumping up a state, a higher state, means I've just swallowed some energy. I need to be in a higher orbital state. Or losing light, what happens when it loses light? Doesn't just go down to a lower orbital pathway. This is when Planck would have actually seen a little quanta of energy escaping the atom and radiating out into the universe as electromagnetic energy. So an electron, a piece of mass, was actually turning into a little electromagnetic wave. And depending on what frequency that light was, is it a red photon, is it violet, is it a gamma ray, whatever it is, it's going to have a different wavelength, different speed, a different frequency, but it's always going to have the same speed. Always travels at 186,000 miles per second. So that was quantum mechanics, except for when they did the math, it didn't work. These orbits did not seem like they were going to be stable. There's just no way that this simple orbital motion, you know, just the way Bohr had it, they were just going in orbits, the way planets orbit the sun. That just wasn't going to work. So de Broglie, kind of on a lark, develops this other theory. He says, you know, what if the orbital behavior of, you know, an electron behaves more like a wave? You know, like it has a frequency and an amplitude and it travels in a wave. Now, this was a big deal because it was one thing for energy, electromagnetic energy, to have the characteristic of a quanta or particle or packet. So energy has this sort of particle aspect. But now he's saying that a particle, an electron, also behaves like a wave, has this energy, this aspect of energy that it's expressed as a wave. That's just, once again, starting to carve away at all the physical certainties, because waves and particles are fundamentally different things that behave in fundamentally different ways, right? A particle has velocity and mass. A wave, and it occupies a specific position in space. A wave has, right, an amplitude and frequency, and it propagates over sometimes a very large distance of space. How can these two things be related? That's just seemed like crazy talk, except for his calculations worked. If you used de Broglie's wave mechanics, it explained how the electron is going to stay in orbit. Okay, so far not so bad. Nobody's freaking out really badly over this, except for the fact that the whole nature of energy and mass is being conflated in a very disturbing way. However, it's the uncertainty principle that really discombobulates quantum mechanics. And the uncertainty principle, Heisenberg is looking at de Broglie's wave mechanics and saying, you know what's really interesting? As much as these equations, these sine waves, actually can define the stability for this electron, if you punch in calculations and try to actually understand exactly the position of the electron along that wave or its actual frequency at any given moment, you actually can't do it. You can either get really, really close to knowing the position, and by the way, you can't know exactly the position, or you can get really, really close to knowing the frequency. Can't know both. Oh, well, let's not get all bent out of shape about it. It's probably just us. We probably just can't measure. Not that big a deal. And this is, oh, good, it's working. Come on, do that again. Okay. All right, and this is just, there's a bunch of ways you can describe this that are sort of like thought exercises. And I keep mentioning this word frequency. A wave is an oscillation, right? It has a certain amplitude, that's how high up the wave goes, and it has a certain wavelength. That's the distance between the two peaks on the trough. And the number of times it oscillates within a certain interval of time is the frequency, that's the velocity. So if you give me a specific moment in time or a specific position of the, of the electron within this frequency or along this wave, you actually, look, you almost know nothing. In order, position is down here. Let's wait for it to collapse and get really small again. Position is a singular point. It's a single entity. Once it gets, well, okay, great, you know the position. But frequency, velocity, I need to know how many times the wave is actually doing this. And if you tell me it's just right here, how do I know how often it takes to do this? So if you give me infinite time, a lot of time, then I can really count how many times it's doing this oscillating. I can really get the frequency down. Ooh, but now look how much time I have. Wow, the particle could be positioned anywhere along that. Well, okay, I really want to know the position. I'm going to just now only work about the position. Oh, whoops. Now I can't know anything about the velocity. Okay, so you're kind of getting it. It's like a little thought exercise. So again, this was not like a major psychic meltdown because even Heisenberg was willing to say, when we try to measure where the, the electron is, we got to do things like we got to introduce like photons, because, I can't see an electron without bouncing something off of it. So we're introducing instruments into the system and, we're messing with it. So maybe we're not able to determine the exact speed or the exact position because we're inadequate. Because we just don't know. We just don't have the means of telling. But if you were like a Superman god, don't worry. There's a specific correlated velocity and particle. You can know these things. But then he starts really thinking about it. He starts doing some of the math. And he has a kind of revelation. Oh, no. It's much worse than I thought. This probability is an inherent aspect of the universe. It's actually deeply, deeply uncertain. You can never know the exact position, not because you don't have a good enough instrument. It's because it's not a wave or a particle, it's a wavicle. It never actually just collapses or has just that one particle identity. First of all, one way to think of it is that, is a particle ever still? Can anything ever be still? No, we already knowing that this is a shimmering, moving, sort of volatile universe. So nothing ever could actually stand still to hold a position. So the whole notion, even on that level, just can't be sustained. And this idea that probability is deep, deep into the nature of matter itself has a lot of sort of profound implications. Now, I'm just going to start a sort of basic understanding. We've talked about waves and the wave that's associated with an electron as it's in orbital motion. And on some level, people were thinking, well, that's the wave. That's it. That belongs to the particle. That's its nature. But what if that's just a probability wave, right? That when we're looking at that peak, that means the electron is most likely to be there. Does it have to be there? No. Are there some deterministic rules of the universe that says no electron, you have to be there? Actually, no. Just probabilistically, it could be there. So suddenly, you don't just have the absence of certainty because you have the absence of data. The absence of certainty exists as an inherent feature of the wave particle itself, which reserves to itself at any moment along its merry pathway. It could have from one causal state, say it's on one position, right, in its, well, even though I've just said it's not, let's just say we've located a probabilistic location for the electron. There's nothing in that set of criteria, right, that says in the next second the electron must be here, right? It's projecting from already a probabilistic set of coordinates, and therefore, when it projects to the future, can it be deterministic or certain? Can it know what's going to happen next? No. It can only offer you more probabilities. And actually, these equations ended up being incredibly bizarre. Like, even though there was very, very low probability of an electron being like way, 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 way out at Saturn, you know, probability is in a way infinite. So, you know, it could happen. So this became a wacky, crazy kind of universe that had no true line of causality. A should cause B. Remember, in a nice mechanical universe, I hit something, that's a cause and effect. I hit something, it knocks over. A means B. Suddenly, you have this horrible universe where A might lead to B, might lead to C, might lead to D, might lead to E. Now, Bohr and Heisenberg take this idea and they formulated it into the Copenhagen interpretation. Now, the Copenhagen interpretation is the dominant interpretation, and it's got a lot of interesting aspects. The radical implication of the theory, the really radical implication of the theory, is that it is a wave. The nature of reality basically is complete. Einstein has this hissy fit, and he says, look, you're missing some variables. You can know the exact position. You can know the exact velocity. Your math isn't good enough. Your theory's incomplete. It's crummy. And he says, I'm holding out for a better theory, a theory where one event correlates to one outcome, right? 1 + 1 equals what? 2. It's not, well, sometimes 1 + 1 equals 2, and then, you know, sometimes it's like 3, and sometimes it's 4. No. Because in a probabilistic universe, you never know what's going to come next, because it's like God is playing dice. God doesn't really care what's going to come next. God must be like, you know, choose from a range of options, whatever works for you, and that's fine. However, that is accepted by Bohr and by Heisenberg on a deep level, and they say it can work on a couple of different levels. You can say that the theory's complete. We can't understand the complete. I see what you're saying. You know what? This is too complicated for now. We'll just have to. Apparently, we are having a quiz. Why do you guys think a quiz is so exciting? Oh, she stops talking 4 minutes early. Quiz! You all know where to report.